Hello, everyone. This is Zhuohaung from Indiana University, and today I'm very excited to give a presentation on our recent work, which is investigation of phase distortion on perceived speech quality for hearing impaired listeners. So here's a brief outline for my presentation today. So first, I'll give a brief introduction on our study. Then I'll talk about the methods and subject recruitment. Then I'll talk about the listening study, how we design the study, and I will present the results, and finally I'll draw conclusions. So when we analyze the speech signal in the time frequency domain, usually via the short time Fourier transform, the speech consists of two components, the magnitude spectrogram and the phase spectrogram. And at each time frame, the phase spectrum represents how the various frequency components in the speech signal are temporally aligned. At each frequency, the progression of phase across consecutive time frames represents the temporal fine structure of the speech signal. So phase is a critical component of a speech signal, and it makes important contributions to the intelligibility and quality. The temporal fine structure Q is important to the perception of talker gender, voicing, and intonation. Replacing or distorting the phase information when reconstructing the speech from a spectrogram will lead to degraded speech intelligibility. So motivations on our study are quite straightforward. First, we noticed that many of the existing speech enhancement systems, they only operate based on the magnitude spectrogram and keep the noisy phase unchanged when resynthesizing the enhanced speech using the inverse short time Fourier transform. Recent studies have shown that better phase estimation of the original speech improves both the subjective and objective speech quality, but they have only evaluated on normal hearing listeners. And modern digital hearing aids, it consists of building speech enhancement algorithms to remove the unwanted background noise that corrupts the speech. So it is not clear whether hearing impaired listeners would benefit from the phase preserving speech enhancement systems. Also, the hearing impaired listeners have reported to have poor sensitivity to temporal fine structure and benefit less from temporal fine structure cues for speech understanding. So we infer that it might be the case that preserving the phase information in speech enhancement may not lead to the same degree of benefits for the hearing impaired listeners when compared to the normal hearing group. And furthermore, the objective speech quality metrics developed for normal hearing listeners, such as PASC, may not directly generalize to the hearing impaired listeners. So therefore, it is not clear whether existing speech quality metrics could be adequately used to capture the effects of phase distortion for the hearing impaired listeners. So our study, first we investigate the influence of phase distortion on speech quality for both the normal hearing and hearing impaired listeners. And we assess the agreement between subjective and objective speech quality using two metrics, the PASC and the HASKI. And in terms of how we generate the phase distortion, we generate the phase distortion following the equation presented here at 4 different degrees from 25% to 100%. So the distorted phase is basically using the original clean phase plus some phase perturbations that is drawn from a uniform distribution between 0 and 2 pi. Then we apply this to this phase spectrogram, and we resynthesize the phase distorted spectrogram to the phase distorted speech while using the original magnitude spectrogram. So in terms of our subject recruitment, in total, we recruited 18 subjects, and 10 of them are normal hearing listeners, 8 of them are hearing impaired listeners. Their average auditory thresholds are provided in this table. And all of them are native speakers of English, and we ensure the audiometric thresholds are below 20 dB HL for all normal hearing listeners. So in terms of the listening study, we use the speech utterances from the IEEE sentences that is spoken by a female talker. And also to ensure the speech audibility for the hearing impaired listeners, we applied a standard hearing aid prescription formula, the NALR, used to amplify the speech stimuli. And the speech level was calibrated to 65 dB SPL before we apply any amplification. And all signals were low pass filter at 4 kilohertz to ensure that the perceived speech quality is not dominated by the hearing loss at high frequency bands. So in total, we include 4 different experimental conditions. This includes the noisy condition, where we have the phase distortion, 4 degrees of phase distortion, and the babble noise that is ranging from -5 dB SNR to 10 dB SNR. We also include a noisy enhanced conditions. It's basically applying an IRM, ideal ratio mask, to the noisy condition. And we also include the reverberant condition with the distortion and the reverberation. The reverberation has its tau 60s from 100 milliseconds to 1,000 milliseconds, and the babble noise fixed at 10 dB SNR. We also apply an IRM to introduce the reverberant enhanced condition on the reverberant speech. So in terms of the procedural, we follow the Mushra studies procedural, which includes a clean reference, low pass filtered anchor in the test stimuli. Each trial, the listener click on the buttons to hear the speech stimuli and give a rating, and they are allowed to play the reference and test stimuli more than once. So here's an example interface for our study. Our listeners, they can click the reference to hear the clean signal as many times as they want, and they can also click different audio buttons to listen to the audios with different degrees of phase distortion, different conditions, and also there's a hidden anchor, which is a low pass filter of the reference signal, and a hidden reference inside of the audio stimuli. And they're using this slider to give a rating, and after they finish the rating for all the audios, all the 6 audios, they can click the next button to move on to the next trial. So finally, in terms of the results, so for the noisy condition, we found that higher SNRs, so higher SNRs leads to higher quality ratings, and greater degrees of phase distortion leads to like lower ratings for both listener groups. Also, the hearing impaired listeners tend to give higher ratings than the normal hearing listeners, suggesting that they have higher tolerance for the phase distortion and background noise. So for the noisy enhanced condition, we notice that the quality ratings are generally higher than those of the noisy conditions, indicating that the IRM-based enhancement can improve the perceived speech quality. So a speech enhancement algorithm that is able to reduce phase distortions would likely to lead benefits in perceived speech quality for all listeners. As when we apply the IRM here, we can clearly see a trend that the hearing impaired and normal hearing listeners, they can have a sense of phase distortion as the quality is decreasing. Also, for the reverberant condition, we notice that shorter reverberation times, like the blue bar here, the shorter reverberation times, they leads to higher quality ratings, and greater degrees of phase distortion will generally leads to lower ratings for both listener groups. And long reverberation times, such as the 1,000 milliseconds, could mask the phase distortion applied to the speech and make it less noticeable. And in the reverberant enhanced condition, we notice that the RM-based enhancement can improve the speech quality, which is a similar trend in the previous noisy condition. And following speech enhancement, the effect of phase distortion becomes stronger for shorter reverberation times. So also we did a correlations between the subjective ratings and the objective ratings on the speech quality. So here is the correlation coefficients table for PASC and HASKI under noisy and reverberation conditions, also the noisy condition and noisy enhanced. So we notice that the PASC generally provides closer correlation to the subjective ratings than HASKI, and especially for the enhanced speech. So HASKI does not generalize well with the enhanced speech, as the correlation coefficient is lower than the task. So in terms of our conclusions, so we conclude that the hearing impaired listeners, they tend to provide higher ratings for the same speech stimulus corrupted by either background noise or reverberation than normal hearing listeners. And following the phasing sensitive enhancement, so the ideal ratio mask in our study, the hearing impaired and normal hearing listeners, they can differentiate the degree of phase distortion that remain in the enhanced speech, indicating the potential benefits from phase sensitive enhancement techniques. So we surmise that this hearing impaired listeners may notice the phase distortions because first, they may have good temporal fine structure sensitivity to capture the phase distortion, or the temporal fine structure and phase cues are weighted higher for quality tasks as compared to the recognition tasks. So that's all for the conclusions. And here are the references. And I will thank everyone for your time and attention.